Okay, so the singular value decomposition, section 7.4, and like I said, we're going to let section 7.3 go. That section is it's a nice section, but I think this is actually a little more important. And you know, I want to have it. I want you to take what you've learned in this course and use it in other courses. And this is an important idea. So, what is this singular value decomposition? So you learned about diagonalization, taking a matrix A and writing it as, like for instance, P times D times P inverse. That was section 5.3. And then in section 7.1, if you had a symmetric matrix, you could write the matrix A as P times D times P transpose. And the P matrix there is an orthogonal matrix, so P transpose equals P inverse. And these diagonalization theorems are very important. We already saw in section 7.2 how diagonalization could help us find appropriate principal axes for a quadratic form. But we also know that not all matrices can be factored. For instance, like in section, like if you have a matrix A, and let's say it's not symmetric, let's just, matrix A, some matrix A, some square matrix A, and you want to write it as P times D times P inverse. Well, I want to be careful. The matrix A, in order to express it as P times D times P inverse, it has to be a square matrix. But not all square matrices can be factored that way. And also, what if you have a matrix A that's not square? What if you have a non-square matrix A? Is there a factorization for a matrix A that's not a square matrix? Like, for instance, if you had a matrix A with 2 rows and 3 columns, could you factorize that matrix? Well, you can. They mention here that a factorization where the matrix A can be written as matrix Q times a matrix D times a matrix P inverse, that's possible for any n by n matrix A. A special factorization of this type is what's known as singular value decomposition of the matrix, and it's one of the most useful matrix factorizations in linear algebra. And once again, you've seen how these factorizations, it's how they help us. The LU factorization, for instance, of a matrix A, we learned that was helpful for computing determinants of a matrix A. It was helpful. And we've seen these other factorizations. If you want to take a matrix A and raise it to a certain power, well, the matrix factorization, A equals P times D times P inverse is very helpful. So matrix factorizations, it's absolutely amazing, but they are extremely helpful. And section 7.4 talks about a lot of different concepts. I want to do one nice example, and it's basically example 3 from section 7.4. That's going to bring all the concepts together regarding this singular value decomposition. And we'll actually prove why it's true also from the book. So let me just show you first what a singular value decomposition is. Okay, so let me just kind of keep going here. Hold on. Here, this is what I want. Okay, so a singular value decomposition. Let's say we have a matrix A, that's an m by n matrix, and it has rank R. So what does rank R stand for? Do you remember what rank means? The rank of a matrix? What section did you learn rank in? Do you remember? Okay, good, Eleanor. Good, Caleb. It's the dimension of the column space. So Caleb, right, it has to do with the number of columns. So a matrix A has columns, and those column vectors, okay, those columns are column vectors. And if we were to take all the column vectors and see how many of them are linearly independent, that would be the rank of the matrix A. So in this case, we have a, hold on here, we have a matrix that is an m by n matrix, and it has rank R. So R is, you know, whatever the rank is, okay? R is whatever the rank is. Now, then there exists an m by n matrix given by that matrix. The symbol is called sigma. It's Greek symbol sigma. And maybe let me just okay. So there exists an n by n matrix sigma, okay, in which the diagonal entries are what are called singular values of A. And we're going to talk about all of this, okay? So don't get too confused. This is going to be all clear in a moment. What we want to do is we want to express this matrix A as the product of a matrix U times this matrix sigma times the matrix V transpose. And the matrices U and V are orthogonal. Okay, the matrices U and V are orthogonal. So the V transpose is the same as V inverse. So when they said, hold on here, when they said that the any matrix can be expressed as Q times D times P inverse, they're the product of those three matrices. This is what they're getting at. So I want to go right to an example here. I want to go right to an example and show you how this works. Okay, so let me go ahead here. Okay, what we want to do is we want to construct the singular value decomposition of this matrix A. All right, let me give you a moment to copy the example down. And let me ask you this. Can the matrix A be written as P, can it be factored as P times D times P inverse? Okay, is that, well, I want to be a little bit careful here. No, that's fine, that's fine. So this is like section 5.3. Section 5.3, when you first learn about diagonalization. Can we factor this matrix A this way? What do you think? Is that factorization possible for this matrix A, which has 2 rows and 3 columns? You're right, Eleanor. It's not possible. Why? Why do you think it's not possible? What was the restriction in section 5.3 on the matrix A? All the section 5, good. In section 5.3, you had a square matrix. Okay, so this, you're not going to be able to factor this matrix A. You're not going to be able to factor it this way. And also, you're not going to be able to factor this matrix as P times D times P transpose. Because for that, you would need the matrix A to be what kind of matrix? For this factorization, and that factorization is actually from section 7.1. What factorization, what would be needed for this factorization here? The matrix A equals P times D times P transpose. What's the condition on the matrix A in section 7.1 for this factorization here? Good, Eleni. Very good. It must be symmetric. Well, this matrix A is, well, it has to be square to be symmetric, and it's not even square. So you're not going to be able to factor that matrix this way. But yet, in applications, a factorization of a matrix like this is important. So, okay, there are 3 steps to finding a singular value decomposition of the matrix A. Okay, let's go through them one by one. And I'm going to just outline the steps, and you follow along the steps, put it in your notes, and then I can show you why this all works with a proof at the end. But let's just go through the solution here. Okay, so again, what we want to do is we want to express the matrix A this way. Okay, so the matrix A is a 2 by 3 matrix. Okay, so since the matrix A is 2 by 3, then according to the singular value decomposition, okay, the matrix sigma here also has to be 2 by 3. However, the matrix U and the matrix V, those are going to be orthogonal matrices. So, and the dimensions on the matrix U has to be 2 by 2, because otherwise you couldn't multiply U times sigma. And then the dimensions on the matrix V has to be 3 by 3. Well, a V is a 3 by 3 matrix. So V transpose is also a 3 by 3. And you need that, otherwise you can't multiply sigma times V. Now what we have to do is we have to find this matrix V. We have to orthogonally diagonalize A transpose times A. Now, A was a 2 by 3 matrix. A transpose is a 3 by 2 matrix. So that means A transpose times A has dimensions 2 by 2. We're going to orthogonally diagonalize that matrix A transpose times A. And we can do that because A transpose times A is symmetric. It's a symmetric matrix. Now, why is that true? Well, if you take A transpose times A and take its transpose, then by the law, the transpose of a product of 2 matrices is the product of their transposes in reverse order. So A transpose A quantity transpose is equal to A transpose times A transpose transpose. That gives you A transpose A. So you started out with A transpose A, You took its transpose and you got A transpose A back. That means that that's the definition of what it means for a matrix to be symmetric. Is if you take the transpose of a matrix and get that matrix back, the matrix is symmetric. Okay, so it can be orthogonally diagonalized. Let me stop there for a moment, and let's see if you have any questions. Okay. All right. Let me know if you have any questions. All right. Well, then let's keep going then. Who's feeling good so far up to here? Who's feeling okay? Who's comfortable? Okay. Very good, Eleanor. All right. Well, let's just keep going here. Let's keep going. So we're going to use MATLAB to help us here. Okay, we're going to use MATLAB to help us. Okay, and first of all, we would type in MATLAB the matrix A, and then we would find A transpose A, and we would get this symmetric matrix. The eigenvectors, the eigenvalues and eigenvectors are listed here. Lambda 1, which is the largest eigenvalue, is equal to 360. Okay, and so the unit eigenvector corresponding to that would be a third, 2/3, and 2/3. Okay. So for instance, in MATLAB, you know, if you might get the eigenvector 1, 2, 2, but you just normalize it by dividing by 3. So this eigenvector here is a unit eigenvector. It has length 1, but it's still an eigenvector, right? The second eigenvalue, so the second positive eigenvalue is lambda 2 equals 90. And I'm listing them in this order for a reason. I am saying lambda 1 is the largest positive eigenvalue. Lambda 2 is the next largest positive eigenvalue. Okay, lambda 2 equals 90. And the eigenvector corresponding to that would be equal to this eigenvector. That it's the unit eigenvector. Okay, and then finally, the third eigenvector is lambda 3 equals 0. And then V3 is the unit eigenvector corresponding to lambda 3 equals 0. Okay, are there any questions so far? Okay, let me know, and we'll move to the next page. Just let me know when you're ready. Okay, thank you, Benjamin. Benjamin's good. All right, Eleanor is good. All right, and Eleanor is good to go. Thank you, Eleanor. And all right, maybe one more, and then we'll move to the next page. All right, Christopher, very good. Okay, so what are we going to do with these three eigenvectors? What are we going to do with them? Well, they are used to construct the matrix V. Okay, remember there's the matrix U, the matrix sigma, and the matrix V. And V was a 3 by 3 matrix. So what we're going to do is we're going to construct the matrix V with these unit eigenvectors that came from that are eigenvectors of the matrix A transpose times A. And we note that V is an orthogonal matrix because the columns are the columns V1, V2, and V3. Are they orthogonal? Are these columns orthogonal, V1, V2, and V3? They are, absolutely, absolutely. And that would make sense because we had three distinct eigenvalues, and we learned that when we have a symmetric matrix, that eigenvectors from distinct eigenspaces are orthogonal to each other. We had three distinct eigenspaces, and the vectors in those eigenspaces are all orthogonal. We just normalized them. So V is an orthogonal matrix, and of course that means then that V inverse equals V transpose. Now the next step is to find this matrix sigma. That's a 2 by 3. That's our second step. That's our second step. And the way we do that is we find what are called singular values of A transpose times A. Okay, now what are these singular values? What are these singular values? The singular values are simply the square roots of the eigenvalues. That's what the singular values are. You're not going to get a negative eigenvalue in the problems for section 7.4. Okay. The eigenvalues of A transpose times A will not be negative. It's just a property of that matrix product. So, okay. Let's look at these singular values. So the first singular value, and again, I'm going in order. I take the highest eigenvalue, the highest positive eigenvalue, that's 360. And the first singular value, okay, which is called sigma 1. It's actually sigma, you know, like, you know, this is like a capital sigma here. This is a capital sigma, and this is a lowercase sigma. How many maybe have learned that? Maybe from other classes, these Greek symbols, capitals, and lowercase Greek letters. How many maybe have seen that in another class? Okay, Justin has, Catherine has, absolutely, absolutely. And so sigma 1 is the first singular value, and it equals the square root of 360, which can be written as 6 root 10. So my math lab is going to want you likely to simplify your radicals for these section 7.4 problems. Now it turns out that 6 times the square root of 10 is equal to the length of the vector given by the matrix A times the eigenvector V1. Okay, it turns out that that is true. Now, why is that true? Okay, I'm mentioning this because it is just of some importance, but it's true because if you were to take the magnitude of the vector A times eigenvector V1 and square it, well, you know, that would just equal A V1 transpose times A V1. But then I can put in kind of an intermediate step here. This would just equal then, and maybe I can use my stylus. I've been using it a lot today. This, of course, would equal V1 transpose times A transpose, because A V1 transpose is just the product of the transposes in reverse order. And then you have times A times V1. Okay? So, but what I'm going to do is I'm going to group together, you know, matrix multiplication is associative. So I can group together A transpose A times V1. I can put those in parentheses like I did here. Now, why would I want to do that? Well, because A transpose times A times V1 is simply equal to lambda 1 times V1, because the eigenvector V1 is an eigenvector of A transpose times A, right? So this means then that, well, we have here V1 transpose times lambda 1 times V1. That is just equal then to lambda 1 times V1 transpose times V1, right? I can factor the scalar out of the matrix product. We learned that. And then what is V1 transpose times V1? Well, that's the same as the dot product of 2 unit vectors. That's going to equal 1. Well, actually, it's the, hold on. It's the square of the dot product, right, of 2 unit vectors, of 2 vectors, right? One moment. Got to be a little bit careful here. No, wait. Hold on. Now, V1 transpose times V1 is just the dot product of V1 with itself. And since V1 is a unit vector, it's an eigenvector, but it's also a unit vector, that means the dot product is going to equal 1. And so you get lambda 1. So therefore, because of that, that means then since the norm of AV1 squared equals lambda 1, that means then that if you take the square root of both sides of that, then the norm of AV1 is just going to equal the square root of lambda 1, but that just equals the first singular value, sigma 1. Okay? Are there any questions on this so far? I wanted to, justify this statement here. All right, well, let me know when give me a thumbs up when you're ready to move to the next page, and then we'll do so. All right, Eleanor, thank you. Thank you, Haley. Thank you, Olivia. All right, well then let's go ahead then and move forward. So how many other singular values are there going to be? We found one of them. How many other singular values are there in this problem, do you think? That's right, Benjamin. There are two, because there are two other eigenvalues. All right, so no problem. Well, let's go and get them too. All right. Here's the second singular value, sigma 2, is equal to the square root of lambda 2. That's the square root of 90, which is 3 root 10. And that just equals the norm or length of the vector AV2. And then the third singular value is the square root of lambda 3. That's the square root of 0. Okay. And that just equals the length of AV3. And that's possible, because the third eigenvector has negatives in it, right? So you can end up getting a vector with length 0. Now that we've found the singular values, hence singular value decomposition of a matrix, we're ready to construct this matrix sigma. Okay, and I'd like to talk a little bit about this matrix sigma, but let me give you a moment to catch up here. One moment. Okay, so what's going on here with this matrix D and all this? So what I want to do to make you feel comfortable with this part here is to go to the book and relook at that theorem 10. Okay, well actually, hold on. Yeah, actually what's above theorem 10. So let me just go to the book. We'll come back to this, don't worry. Okay, so you see here, this matrix sigma, the way you construct it is you have a D matrix on the top left-hand corner here. Maybe I can, here's the D matrix on the top left-hand corner. And that, hold on here. Are we showing up good here? Hold on. Yeah, that matrix D is a diagonal matrix for some R, for some value of R. Okay, so the value of R is equal to the number of singular values of A, the singular positive values of A. Sorry, the singular positive, well, the singular values of the matrix A, okay, are the square roots of the eigenvalues of the matrix A transpose A. So actually, let me go back into the notes here. Well, all right, and you notice that they have their m minus r rows and n minus r columns. So let me justify those blue comments there. Hold on, let me go back here. Now that you've seen that, let me go back into the notes here. Okay, and there's one correction here. I should have just singular values of right here. Okay, this should be just singular values of A. I put A transpose A. That's not right. It's the singular values of just A. Okay, so please, if you would correct that in your notes. Okay, and I'll correct it in my notes also. All right, so let me just see here now. I want to, right. So, okay, so now here's the matrix D, and we had remember two positive eigenvalues, right? We had two positive eigenvalues. So that means we have two positive singular values. The positive singular values were 6 root of 10 and 3 root of 10. And those go on this diagonal matrix right here that I've circled. It says D, right? That stands for diagonal matrix. But then the matrix sigma has to be a 2 by 3 matrix. So that means we got to fill in the other part. And we fill that part in with zeros. Okay, now the zeros consist of one column, and that makes sense because it said n minus r columns. Well, n is that there were, in the matrix A had 3 columns, so n is 3, and we had 2 positive singular values. So 3 minus 2 is 1. That equals 1 column, right? 1 column. Okay. Now, in terms of rows, so again, in that above theorem 10 there, when they talk about the matrix sigma, you construct a matrix sigma with the D here in the top left-hand corner, And then you have zeros everywhere else. Zeros everywhere else. Okay. Now, this big zero here means there could be a lot of zeros. It isn't just one zero. This big zero here that is written here, and the zero that's written here, and the zero that's written here stands for a bunch of zeros. Okay. We know that we have just one column of zeros here by virtue of this fact here. And in regards to the number of rows of zeros, the rows of zeros would be here, right? This is the rows of zeros. But you notice there's no row of zeros here. There's no zeros underneath this diagonal matrix D. There's no row of zeros. That's because M is 2 and R is 2. 2 minus 2 is 0 rows. Okay, so I wanted to, you know, this is how you construct the matrix D. Okay, and R again equals 2 because we had 2 positive eigenvalues, hence 2 positive singular values. Are there any questions up to here? Any questions up to here? Who's, you know, who's feeling comfortable so far? Maybe give me a few thumbs up and we'll move forward. Catherine's good, wonderful. Okay. Well, so we found the matrix V. We found the matrix sigma. Now we got to find the matrix U. The way you find the matrix U is the entries of the matrix U are defined this way. The first entry of the matrix U, or I should say the first vector, is equal to 1 over sigma 1. That's that singular value, which would be the 6 root 10, times the vector AV1. Okay, and the second vector, column vector of the matrix U, would be 1 over the second singular value, positive singular value. It has to be positive, right? You can't divide by 0, all right? And then that is 1 over sigma 2 times AV2. So the vectors U1 and U2 I've computed here using these definitions. Let me give you a moment to copy that, and we'll see if there are any questions. Okay, now this matrix U is actually going to be orthogonal. It's actually going to be an orthogonal matrix. Okay, you can see based on the vector u1, what's the length of the vector u1? What's its length? Hold on here. That's right, Benjamin. It has length 1. And the vector u2 also has length 1. Are the vectors u1 and u2, are they orthogonal as well? They indeed they are. You take the dot product, you get 0. That's right. Very good. Now you might wonder why would that be true? Why would that be true? I mean, you know, really what we need to do, orthogonality of the vectors u1 and u2 is dependent on the vectors av1 and the vectors av2. The dividing by the singular value sigma, all that does is scales those vectors, but orthogonality depends on what direction the vectors point. So we need to study the vectors av1 and the av2. And there's a theorem 9 that where this is not hard to prove. It's not hard to prove that the basis of vectors given by av1 and av2, it's not difficult to prove, that's av2 there, not difficult to prove that that's an orthogonal basis. So I'd like to show you theorem 9 in the book just for a minute. Are there any questions on this here? We're almost done with the problem. We're almost done with the problem, but are there any questions at all? All right, let me go here to theorem 9. Well, is everybody done copying this page here before I go to theorem 9? Want to make sure. Just give me a thumbs up when you're ready. Okay, very good, Eleanor. Very good, Benjamin. Okay, all right. Very good, Abby. Excellent. Okay. Okay, so theorem 9. Let's see here. Theorem 9. Okay, this is the theorem. So what this theorem says is, suppose that you have a basis of vectors that are eigenvectors of A transpose A, and you arrange the vectors so that the corresponding eigenvalues satisfy the, lambda 1 is greater than or equal to lambda 2, which is greater than or equal, and so forth. So you arrange the eigenvectors in descending order in terms of their values. And you're supposing A has non-singular values. What I want to really show is that the basis of vectors given by, let me just see here, hold on. the basis of vectors given by AV1, AV2, AV3 up to AVR is an orthogonal basis for the column space of A. Okay, so you know, rank of A is equal to R. So the rank, that's the rank of A is the dimension of the column space of A, and they're saying that there are R that the column space of A, there are, well, the dimension of that is equal to R, so there are R linearly independent that span the column of A. Yeah, Justin or Gavin, question? Okay, okay. So this is not hard to show. This is really not hard to show. If you were to take the dot product of the AVI transpose with another vector AVJ transpose, okay, you could write that as V1 transpose times, well, hold on, let me do it a little more. Hold on. Oh, did we lose the book? Hold on, let me get the book. Hold on. This happens sometimes. Hold on. There we go. Hold on now. Wait. Hold on. Hold on. Okay. So let me do this again. So if you take AVI transpose, okay, and multiply it by AVI transpose of that vector times the vector AVJ, that vector, that would just equal then the transpose of a product is the product of the transposes in reverse order. So you end up getting this here. Let me see. Can you, who's having trouble seeing the screen? Or who's able to see the screen okay? Let me know. Black for you too. All right, hang on. Okay, hang on. We'll fix that. One moment. Just give me a moment. Give me a moment here. I think I know what I need to do. Let me just log out and come back in. What I mean is with the book. Okay, hang on here. We'll get there. One moment here. One moment, everybody. Okay, let me share this again. Okay, is the book visible now in the on the screen? Maybe give me a thumbs up if you can see it. Good, good. All right. Catherine, it's the disappearing book, I guess, you know, but that's okay. We made it appear again, right? Okay. Who else is seeing the book? I'd like a few more, maybe a few more confirmations that you can see the Theorem 9 there. Thank you, Caleb. So if we take the dot product of the vector AVI with the vector AVJ, we're going to end up, well, you know, again, the vector VJ is an eigenvector for A transpose A. So we can write A transpose A times VJ just as lambda J times VJ. But the eigenvectors VI and VJ are orthogonal to each other because you have an orthonormal basis. So that equals 0. So the vectors then U1 and U2 in our example, which were scalar multiples of eigenvectors AV1 and AV2, they would be orthogonal. Okay. Now, in fact, you'll have there'll also be a basis for the column space of A, because if you think about AV1, the vector AV1, A times the vector V1 is really just a linear combination of the column vectors of A, right? When you take a matrix and multiply it by a vector, the components of the vector are really, I mean, in other words, what I'm trying to say is this: if you take, you know, A times V, okay, and the matrix A, for instance, consists of column vectors A1, A2, and the vector V, consists of, say, components, I want to be a little careful how I write it. Let's just say C1 and C2. That just equals what? What does that equal? Something plus something. What's going to go here? What's going to go? Who can maybe chat it out for me? And for our matrix, we had a matrix of rank 2. How do we multiply these two? So this is a, you know, like a 2 by 2 times a 2 by 1, right? What I'm trying to say is, what is, well, I'll give you a hint. I'm going to put a C1 here. What's going to go here in this spot? That's right. That's right, Benjamin, C2. And then here you're going to have A1 and A2. How many recall that this is when you have how many recall that this kind of, I mean, you know, you have a matrix A times a vector V that is equal to this. How many recall that those are equal? It's been a while, right? You learned that back in chapter 1, actually. But how many does that ring a bell? Does that seem familiar? I'd just like to. Benjamin recalls it. How about anybody else? I'll sleep better if I can have a few more responses on this. Okay, good, Catherine. Very good. Thank you. And so the point is, thank you, Abby. Very good. Thank you. So the point is that AV1, like for our example, and it really, it's, based on, I mean, this is really what Theorem 9 says. The vectors AV1 and AV2, okay, those vectors are on an orthogonal basis for the column space of A. Our matrix A had rank 2, so there are two linearly independent, well, the matrix A had rank 2, so these two vectors here are in the column space of that matrix A, because these two vectors are simply linear combinations of the column vectors of the matrix A. Those vectors then would be in the column space of A. So indeed, the vectors AV1 and AV2 would form an orthogonal basis for the column space of our matrix A. And if we normalize those vectors, we'll get then an orthonormal basis. And that's why, if I go back to back to our example, this is why that once we have U1 and U2, that we're ready to construct the matrix U. And it's an orthogonal matrix as well. And below, I just wrote down the comments basically that I emphasized. And we have it. We have our singular value decomposition. We have it. So let you copy this page down. And let me know if you have any questions, please. Okay, and I'm right here if you have any questions. Okay, and when you're done, maybe give me a thumbs up, and then we'll move on. We're almost done here. Almost done. Okay, Abby's good. All right. Okay, Benjamin's good. Very good. Okay, Natalie's good. Very good. Okay. All right. Well, then let me bring up the ebook again. One moment here. Okay. So the proof for this singular value decomposition, they give a proof in the book. I think once you've done enough, you're going to have a little practice, right? Some homework. You'll feel comfortable with this. If you want to look at the proof, I'd be, happy to discuss the proof with you at office hours. They give a proof. They give a proof here, but it is somewhat complex. I mean, basically now you're almost at the point of either senior level in college or a graduate school in terms of like your linear algebra skills. You're getting close to like the next level, okay? But the proof, I'll let you look at the proof if you want, and if you want, I can talk about it with you at office hours if you like. I want to show. Just feel free to see me at office hours if you want to go over the proof. Not a problem. I want to actually mention too, in the book we did example 3 here. We went through example 3, but they also have an example 4 as well, and they're doing a singular value decomposition of a 3 by 2 matrix. And then of course you can do a singular value decomposition of a 2 by 2 matrix. So in the homework for section 7.4, there are 6 problems. 2 of them are just find the singular values. The other 4 are ones where you'll do this process. But they're small matrices. It won't take you long, and you may use MATLAB to help you get your eigenvalues and eigenvectors. Okay. Of A transpose times A. You can use MATLAB to help you. On the exam, final exam, you will be allowed to use MATLAB to help you for section 7.4. Okay, I want to mention one more thing here. Just give me one moment. Okay, let me bring this image up. This is a nice little thing to share with you since this is our last lecture, right? Today. Next week it's final exams. Okay, so what you have here. Okay, so why are things like singular value decomposition useful? The concepts in chapter 7 useful? It had one key application is called principal component analysis. So what they've done, and I want to just kind of keep it very simple here. They have an image, and an image, you can look at different bands of an image. And this image, what they've done, I'm focused on D through F here. So this is a this is in your book, but Earth Satellite Corporation of Rockville, Maryland, is supplied these photos. And what it is, you see, you have an image. The image is an image in Railroad Valley, Nevada. This is a valley. And, you know, when satellites take an image, you know, there's a lot of data, right? There's a lot of data. So what we can do is the data can be stored in a matrix. And the matrix can be essentially by knowing eigenvalues and eigenvectors, you can basically break the image up into like different components, what are called principal components. So like for instance, in D, that principal component, it has 93.5%. That means that 93.5% of the variance present in the data is explained in that picture. Okay, so you know the data, of course, the data varies, right, in the image, but because you have different parts of an image, but there's a key component that explains 93.5% of the picture. And then for E, there's a principal component too that explains 5.3% portion of the picture. And then in F, there's another component which is 1.2% of the picture. So essentially, and again, this is something that some of you will learn later on. By understanding the eigenvalues of the eigenvectors of a matrix, and a matrix could be, you know, like a set of values stored in a matrix, an image. And they actually talk about this in section 7.5. It's just, you know, we just didn't have time to get to it. But if you look at example 4, they talk a little bit about this, and they show you how the eigenvalues and eigenvectors are used to create these different components. So like you know, if you can break the data down, if you can reduce it so that you only need some of the data to get a reasonable enough image, like in D there, in D, you know, I'm 90, like the photo of the valley, 93.5% of the image is explained by that principal component, which is based off of, you know, an eigenvector, eigenvalue, so to speak. You know, it's just a way. How many have heard of like data analysis You know, data analysis, taking massive amounts of data and organizing them to create structure. How many have heard of that? Creating, yeah, Benjamin's heard of it. You know, so this is what you're learning. What you're learning in chapter 7 will ultimately relate to. And you know, I wish I had time to go to cover it with you, but at least you have the tools now to understand that when you encounter this in applications, you'll understand what it means. Are there any questions? Okay, how many think what you learned today is pretty cool? Pretty cool. How many liked what you learned today? Oh, excellent. Justin likes it. Eleanor likes it. Okay, wonderful. Oh, and Justin, I was wondering, Justin works at NIH. Side comment, Justin had a comment here. Hold on. Justin says, evolutionary biologists use principal components to make trees of life that connect species. Wow. Okay, so there's another application. And Justin sees it at NIH, right? So thank you, Justin, for that. Thank you. Okay, let me stop there. Let me stop there. I'll stop the recording. Excellent.